All right, y'all, so 9.7, it deals with growth and decay. So growth and decay. And really, these are just going off of those exponential graphs we were doing the other day. These are applications where you can actually see where you might use them kind of formulas at. So I'm going to give us some formulas to start off with. So the first formula is for exponential growth. All right, so the formula for exponential growth is P of t equals P subscript O times e to the exponent k t. So let me explain what everything is. Now this, they're using p's because a lot of times when you deal with exponential growth, you're dealing with populations. So the P subscript O is the initial amount or population. E is Euler's number, which we learned about. K is what we call the growth rate. So that's the growth rate. Or later it'll be the decay rate when we look at the decay. And then T is going to be time in years. And then the P of T we got over here, that's the amount or population at any time T. So that's the amount or population at any time T. All right, so I'm going to give you another formula for exponential decay, and they're pretty similar. Now you'll see decay when they talk about stuff in chemistry like half-life. Okay, like the half-life of uranium, you would use this kind of formula. So they're basically the same. This is P of T equals P initial e to the negative K times T. So the only difference on the two formulas is the negative in front of the growth rate. In this case, we'll call that the decay rate. Okay, so everything else is basically the same. Initial amount, decay rate, T is still time in years, and then this will be the amount left at any time T. All right, so the last formula I'll show you is what we call the double time. And this is the amount of time it takes for the population or the amount to double. So this would be a capital T equals ln of 2 divided by K. So now I got the capital T that represents the double time. K is your growth rate. Just remember, if I give you the growth rate as a percentage, you're going to have to turn it into a decimal when you put it into my formula, okay? All right, so let's see, that's my three formulas. And then half-life, which goes with the decay, would be the same formula, okay? You'd have the growth rate, ln2, and then a capital T for half time. So let's work some of these problems. So this first example, they're telling me in the year 2012, the population of a city, so the population is 5.38 million. The exponential growth rate is 3.85% per year. So there's four things they want us to find. So A, they want to find the exponential growth function. All right, so they're going to give you P of T equals, and then we got to find everything else to put into the formula. So when they say find the exponential growth function, they just want the general formula that we would use on this problem. So 5.38 million is my initial amount, so that's going to be our P of 0. And then really the only other thing we need is we got 3.85%. We need to turn that into decimal form by moving that decimal left twice. So if we move the decimal left twice, we're going to have to add a 0 so that we get a 0.0385. All right. And then our variable for T will still be our time, okay? So here we go. We're putting in our initial amount, which is 5.38. Then we got our Euler's number, E. Our exponent is K times T. Well, our K is the growth rate, which we said was 0.0385. And then we'll multiply that times T, so that we could use this formula to find what the population would be after T amount of years. All right, so y'all, that's what they wanted us to do on that. Part B, estimate the population in the year 2018. So we're going to use this formula right here. So we got our P. Since the year is 2018, we need to figure out what is the T going to equal. So our initial year was what, 2012, and we're looking at 2018. So we're going to take our 2018 minus our 2012. 6. And what y'all just say?
6.
Okay, 6. There you go. Which means we're finding P of 6 on this equation. So put in your 5.38 E 0.0385. That's going to get multiplied by 6. All right, y'all, these are wanting me to round these one decimal place when we get our answer. And y'all, really, I just plug this in on my calculator as it looks. I got my 5.38. Remember, to get the E with the exponent, you hit second ln. That brings up the E with the exponent. And then we do 0.0385 times 6. And then remember, we're rounding this 1 decimal place. So that's what, 6.77. I'll make that what, a 6.8. And remember, that's actually in millions. So if you notice, in those 6 years, this little town or city or whatever we're looking at, they grew almost 1.5 million people. All right, so y'all got that? All right, part C of that. The population will be 8 million in about blank years after 2012. All right, so we want to know when will it be 8 million. So we're looking for the T on this equation. So since we're looking for the 8 million, that's going to be my final amount. So I would put my 8 million in for my P of T. And then our equation was 5.38 e to the kt. My k is still 0.0385 times t. So in this formula, we are solving it for the t now. So it goes back to the equation you just finished doing in 9.6. So, I'll tell you, the first thing I would do would divide both sides by the 5.38. So let's divide both sides by 5.38. That way we'll have our e to the exponent by itself. So 8 divided by 5.38 is going to give me basically 1.487. So I'm just going to round out about 3 units on here. But on this side, all that's left is e to the 0.0385 t. So at this point, we need to bring this exponent down. And the way that I can do that is by taking a ln of both sides. So remember, anytime you got an e with an exponent and you need that exponent brought down, you need to take the ln of both sides. So the ln of 1.487 will equal the ln of e to the 0.0385 t. But y'all remember, this log base raised to the base that matches with an exponent, the right side is just going to equal the 0.0385 t. Okay, so when you take the ln of e raised to an exponent, it's just going to equal that exponent. And now on this side, we still have our ln of 1.487. All right, we're almost there. My last step, I need that to be a 1t. So at this point, we're going to divide both sides by the 0.0385. So 0.0385. All right, so here we go. I'm going to do the ln 1.487 888688848. I'm just punching it like I have it on my screen here, so I can make sure I'm going to be accurate. So close parentheses and then divide that by the 0.0385. Now this, they want me to round one decimal place. So that's going to equal my T. And y'all, that's pretty close to what, a 10.3. So in 10.3 years, the population would go from the 5.38 to the 8 million. So not too bad. They gained what, almost 3 million people in about 10 years. All right, so for part D, the doubling time is about blank years. So remember, I gave you a formula for the doubling time. The doubling time was capital T equals the ln of 2 divided by K. All right, so ln of 2 will be on top. We have our K we've been using, which was what, 0.0385. So y'all, if we figure that out, we'll have our doubling time. So here we go, ln of 2, close parentheses, divided by 0.0385. And that looks like I'm going to get and this is going to be one decimal place. So that's what, a 18.0 years. So in 18 years, this population would go from 5.38 to 10.76, I guess. All right, so that was an example doing exponential growth. So questions on that?
No.
Yeah. You said no, right?
No, yes, I don't have questions.
All right, so this one, they want us to complete the table. So my table is going to have population in the first column, growth rate in the second column, and then doubling time in the third column. So they have country A and country B. Now, country A, they're giving me its growth rate is 1.9% per year. They're not giving me the growth rate of country B. And on the doubling time, they're not giving me country A's doubling time, but they are giving me country B's doubling time is 46 years. So we're looking for the growth rate of country B and the doubling time of country A. So I guess I'll find the doubling time first for country A. So remember, the doubling time is a capital T. And now I'm just going to put a little a under there because I'm finding the doubling time of country A. So that's going to be ln of 2 divided by my growth rate. But remember, my growth rate is 1.9%. Y'all need to turn that into decimal form by moving that left twice. So we get what, a 0.0?
0.019.
There you go. And then that's what you're going to put into your formula. All right, let's see on this one. We're going to round doubling time to the nearest whole number, and then we'll round the growth rate on that problem to the nearest tenth. So the nearest whole numbers, let's see what we get. We got an ln of 2.
4.
Divided by 0.019. So what's that going to be to my nearest whole number? That's just going to be what, a 36? So it's going to take 36 years for that population to double. So in the little blocks, you just put a 36 in for that one. All righty, now we got to find the growth rate for country B. So we know that the doubling time, which is 46, is going to equal ln of 2 divided by RK. So basically, on this problem, since I'm solving for the K, I would multiply both sides by K to start, because that'll give you a 46K on the left side, which on the right side, the K's cancel, and we're left with the ln of 2. So now we got 46K, we need that to be a 1K. So now we divide both sides by the 46. So basically, all I did was flip-flop that T and K on this formula, okay? So notice these 46's cancel and we get our K. Now we got ln of 2 divided by 46. So that's going to give us a 0.015. I'll go out of 07 for the moment. But y'all remember, growth rate has to be like a percent. This is in decimal form. So we got to do one thing to this. Since we moved our decimal left twice, so you're going to move it to the right?
Twice.
So now we said this has to be to the nearest tenth. So that's going to be what, a 1 point, looks like it's going to stay at 5. And then throw our percent. Now, when you do this on the MATLAB, they already got the percent, so all you're putting is the 1.5. All right, y'all good on that one? So just remember, we're basically using our, we're basically using that double time formula, okay? These aren't too bad. You're just having to always use them same formulas. So the third one, y'all remember we've been dealing with interest a lot. We did simple interest. We did compounded interest. You can also use these exponential growth when you got what we call continuous compounding problems. So we're going to suppose that $17,369 is invested at 6.6% compounded continuous. So for A, we're going to find the exponential function. That describes the amount after t years. All right, so we're going to find our function that describes the amount after t years. So we got our initial amount. So my initial amount is this 17,369. We got our K, but we need to convert that into a decimal form. So I'm going to move that decimal left twice so that that's going to give us a 0.066. So that'll be our K. And y'all remember, that's all I need for the first question to find out the actual exponential function. That's going to be P of t equals our initial amount, which is 17,369 times e to the k times t. In k, we said was 0.066 times our t. So now if they give me years, I can find out what amount is actually in my investment. All right, B says, what is the balance after 1 year, 2 year, 5 years, and 10 years? So we're actually going to use our formula now to find the 4 different amounts they asked. So for 1 year, that'll be P of 1. So that'll equal 17,369 times e to the 0.066 times 1. So these, let's see, we're going to round 2 decimal places, which basically would be to the nearest cents. And think about this. This is investments, so these amounts should be going up, okay? So y'all, let me show you 2 ways to do this. First way is just to punch it in, 17,369. Get the E with the exponent, that is second ln. And then I do 0.066 times 1. All right, rounding to the nearest cents, basically, looks like $18,554 and 0.0. Yeah, it looks like a 3. There you go.
Right.
Okay, so I'd be happy. That went up about $1,000 after a year. Next, we would do P of 2. So that'd be 17,369 raised e to the 0.066 times 2. So I'm expecting that should be a little bit bigger than the 18,000. So here we go, 17,369. Second ln to get my e, 0.066 times 2. So y'all, that one we get what, 19,819 point.
91.
Now, y'all see how we're doing these one by one, right? Let me show you an easier way. I'm going to use my graphing. So let me go to my y equals. Now I'm going to clear this out. And I'm just going to put our basic function in here. Except instead of a t, I'm going to use an x. Okay? So here we go. 17,369. Second ln to get my e. And then 0.066x. So when I graph them, or when I look at the table, I want to use x's instead of t's, okay? Now, I'm going to go to the table. So I'm going to hit second graph to get my table. So let's see, down here at year one, there's my 18,554. Now, I want y'all to see, it don't give you the decimal up here, but look down here. Here's the 18,554.029 that I got on the calculator a while ago. So when you highlight the y value, it will give you the decimals you need. And then when I went to 2, notice it don't give me the value yet, but when I click on the y value, there comes my 0.91. So if you hover on the y value, it'll give you them decimals exactly. So watch this. What was next? P of 5. So we could punch it in as a 17,369 e to the 0.066 times 5. But y'all watch this. I can go right to the 5 on this calculator for the x value. Hover on the y value. And that'll give us $24,159. And oh, I can't hardly see that, but that looks like what, a 7? Is that a 2 after the 7? So that'll go to a 3. So I get $24,159.73. So we're starting to make money on this. Now, 10 years. So that'll be P of 10. So 17,369 e to the 0.066 times 10. So let me go over here. I can go down to 10 now. Hover on that y value, and I get $33,605. And I'm going to go with what, 41 cents.
1.
So I really love the calculator on those because I can put those formulas into y equals and then find all the values I need as I go through there, okay? All right, y'all, this has a part C. So part C says the doubling time is blank years. All right, so we know our doubling time formula. That's a capital T equals the ln of 2 divided by RK. All right, so we got our ln of 2. We've already turned K into a decimal, right? That was what, 0.066? And y'all, this one we're going to round it 1 decimal place. So let me clear that screen. ln of 2, close parentheses, divided by 0.066. So that's going to be, what, about 10.5 years. So that makes sense because at 33,000 at exactly 10 years was pretty close to being double. So double that would be 34,000 something. So it's pretty close, but continuous compounding can double your money in 10 years versus when we were doing the semi-annual compounding and quarterly compounding. Those grew at slower rates, okay? All right, questions yet, y'all?
Nope.
All right, so it looks like I got time for another good one here. So let's see. So this one says there are currently 69 million cars. So currently 69 million cars in a certain country, decreasing by 5.6% annually. How many years until there are only 46 million cars? So this is what we call exponential decay. So remember, my formula for exponential decay was P of t equaled my P initial e to the negative k times t. Okay, so our P of t is going to be the ending amount. My PO will be the starting amount, which was the 69 million. And then our K, we're going to have to turn that percent into a decimal. So let's see, if we move that left twice, that would give us a 0.056. So what we're looking for on this one is the time, or the t. So the ending amount we said was 46 million. That's going to equal the beginning amount, 69 million, times e to the negative k. Oh, what did we say k was, y'all? That was 0.05.
0.05.
And then that's going to be multiplied by
T.
or t. There you go. And we will work this one similar to the way I did that first problem. The first step you want to do is divide by the PO, which is the 69, because we want to get this E stuff all by itself. So our first move is to divide them both by 69. So 46 divided by 69, ooh, that's going to be 0.666. I'll just round that to a 7. But on this side, you get E to the negative 0.056 T. All righty. I need to solve that for the T. So what's your next move?
Make it ln.
ln, there you go. So the ln of 0.6667 will equal to ln of e to the negative 0.056 t. So I'm just going to leave the left side as the ln of 0.6667. So the right side, we're taking the ln of e, which means that's a logarithm base e raised to e to the exponent. All that's going to be left is the exponent, because the ln of e part turns into a big 1, remember? Alrighty, so I got ln 0.6667 equals a negative 0.056t. One more move, y'all, and we're done. And that's to divide them both by the negative 0.056. So let's see what happens. So the ln 0.6666, I'm just going to do a few more sixes than they did. Now, if you notice, when you do the ln of 0.666, you get a negative number. But we're now dividing by negative 0.056. So that negative is going to divide by negative, making this a positive. And we're going to round to the nearest year. So there's my t. So that was what, 7.2. So the nearest year would be a 7. All right, y'all good on that?
Yes.
All righty. All right, y'all. So this one, they're giving us a table here. So they're going to have a year and percent of adults.
Mr. Rathbone?
Yeah.
Mr. Rathbone?
Yeah, I hear you.
Why did you, when you were doing why did you add all the extra sixes in the 0.6666667? What was the reason for that?
Yeah, I was looking at my calculator here, and they had all these sixes coming out across it. And so I was just trying to keep it as accurate as I could on that by going out more decimal places.
Okay.
Sometimes if you round them off too.
That was the answer to the 46 divided by, that's the answer you got for 46 divided by 69.
Yes, ma'am.
Okay, so then you just use that.
Yeah, and see up here, I just rounded it off to a 0.6667, but I wanted more accuracy, so I started adding them things back in there.
Okay.
Mm-hmm.
All righty.
All right, and let's see. This looks like this has a year 1960, 1980, 2000, 2010, and then 2012. So this is percent of adults who are married. Percent married, I guess I'll put that. So we had 68.2, 62.2, 54.3, 46.1, and then 43.5. All right, so there's my data. So it looks like less and less people getting married, at least, from this data, right? So for part A, they want us to use data for 1960 and 2012 to find value of K. So basically, we're going to have to put this back into a formula. So remember, 2012 will be my P of T. 1960 will be my P original, okay? So you would put in your 43.5. That's going to equal your original amount, which was 68.2. E. We don't know K, that's what we're looking for. And we know since it's decay, it's going to be a negative K. So we got to figure out what is the T. Well, T is going to
52.
be, how many did you say?
52.
There you go. And y'all, she just did 2012 minus 1960. Alrighty, so we're going to solve this. Remember, our first step is to divide both sides by the 68.2. Because we need that exponent brought down. So 43.5 divided by 68.2 is basically a 0.6378. That's going to equal my E to the negative K 52. Alrighty, so I need to bring that exponent down. So I'm going to take those LNs of both sides. All right, so I'm just going to bring down the LN 0.6378. But I know on the right side, the LN of E is going to become a 1, so that this just becomes a negative. And I'm just going to put them in order and just make that a negative 52K. Which means last step, divide both sides by negative 52.
52.
Negative 52.
All right, so let's see what that gives me. So LN. Now, if you want to be really accurate at this part, you can do LN 43.5 divided by 68.2. Get that answer. And then divide that by the negative 52. So these negatives are all going to make this into a positive 0.00. Well, what's that next number? I can't see, y'all. 0.00.
864.
Okay, so let's see. They want us to round 4 decimal places, so that'll be 0.00. You said 864? So that'll be
86.
86. There you go. All right, so the next part, they wanted to write an exponential function. So on this one, they'll have an m, a t equals blank e to the blank. So, and I guess they're using M on this one for marriages. So a lot of times they'll have the letter that represents what they're sort of looking for, like whether it's population. In this case, it was marriages. So our initial amount on marriages was our 68.2 up there. E, remember this is a negative because it's a decay. All right, what was my K? 0.0086, and then I'll have a T. So for any year T, I can find the percent of people that would be married. All right, y'all good? So I'm going to go to the next part of this.
So with the T, you said any year T, would that be the number of the year or how many years since the
How many years since that 1960?
1980 would be 20. the T would be 20.
Yeah, there you go.
Okay.
So knowing that, estimate, so we're going to estimate percent married in, oh, that is it, 2015 and 2018.
Sorry, sir, can you put the page down? We can't see it.
All right, you good now? So we're going
Yes,
to
sir.
estimate the percent married in 2015 and 2018. So let me put our formula back up here. We had M of T equaled 68.2 E to the negative 0.0086 T. So what I need to know, y'all, to do 2015, how many years is it from 2015 starting at 1960?
$55.
55. So we're going to find M of
$55.
55. So that helped you on that, Carol?
Yes.
That's pretty much what you was asking, I think, on that.
Right.
Right. So we got 68.2 E to the negative 0.0086 times 55. Now, I'm going to be happy if I get a number less than 68.2 because it looks like this has had a decay rate. So you always want an amount smaller. So here we go, 68.2. Second, ln to get my E. And then I got negative 0.0086 times 55. Or remember, you could have graphed this in y equals and found both of these amounts pretty quick. All right, y'all, so let's see. I'm going to round this one decimal place, so that looks like 42.5%. Ooh, okay. So now, what was my second year? 2018, I said. So for 2018, so remember, this was 2015 here, and then this will be 2018. So it looks like I'm going to add 3 more years to that, right? So instead of 55, this will now be M of 58. So 68.2 E negative 0.0086 times 58. All right, so this should be even less. So y'all, what is this? This is like 19, this is 2020.
2018. 41.4.
So 41.4, perfect. So, I'm betting it's probably going to be less than 40% for today's days, huh? All righty. So the last question we'll have on this. At this decay rate, in which year will percent of adults married be 30%? So remember, since we're looking for when something will be 30%, that 30% will be my ending amount. My beginning amount was what? 68.2 E negative 0.0086. But this time we're looking for the T. Now remember, I'm looking for the year. So when we find our T, we're going to have to add that back to the 1960 that we started at, okay? All right, so we've done these enough now that we're going to start out by dividing by the 68.2. So let's see what that'll give us. 30 divided by 68.2 is basically a 0.4399. I'll just call that a 4399. That's going to equal our e to the negative 0.0086 t. All right, so y'all know the magic move now. ln of both sides. Which means this left side is going to stay ln 0.4399. That's going to equal that's going to equal what? Negative 0.0086 t. All right, y'all, last move, divide both sides by negative 0.0086. And that'll give me a t there. So here we go, ln. And remember, if you wanted it more accuracy, you could redivide that. You could do 30 divided by 68.2, close those parentheses, and then divide that by the negative 0.0086. Whoa, that's giving me t equals round to the nearest whole year. So that looks like, whoa, that's going to be 95.
Okay.
Remember, that's not my answer. I need that in years. So take that 95 and add that to the starting amount, which was what I say,
1960.
1960.
1960.
Uh-huh. So it looks like the year is going to be the year 2055. So y'all, only a third of the people in whatever country we're looking at going to be married in 2055. So they must not be liking each other as much, huh? Alrighty, so if you want to see some exponential graphs these days, you can look on TV at the COVID stuff, because those are really nice exponential graphs. And they're going up pretty quick. Alrighty, so y'all, what we'll do Wednesday, we're going to review for test 4, okay? And then I'll open that up. And then the rest of the year is going to be studying for the final.
All right.
Sir, are you
That's
going
good.
to
Say again?
give us some more exercises for reviewing for the whole year? Are you going to provide us with some exercises to do, or?
I got a online final exam I'm going to be putting on there, a final exam study guide. And,
Okay.
and that'll let you go through it as many times as you want. And it'll be pretty much the same as what I'm going to review y'all with, okay?
Awesome. Okay.
So I'm going to start getting all that ready this week for you. And I'll be finding a bonus to send probably tonight or tomorrow for y'all, okay?
All right.
Thank you.
All righty, y'all. So I'll end this and then I'll get our